Hello, students. In the last class, we had discussed about reflection, refraction of light. As I already told you, today's session will be of drawing images. We are going to draw images for different object position. So let's begin with it. Hope you remember what was done in the last class. So last class we had discussed about refractive index concept. Then we started with the lens, the types of lens, convex, concave, how the rays get refracted through lens. All that was done in the last class. So you can just revise it before you start seeing this video. Yes. So today we are going to get the images for different positions of objects through lens. Okay. So first I'm going to take convex lens and I'm going to place the object in front of convex lens at different positions. And I'm going to see where I'm going to get the images for those positions of object. But the problem is, to get the image, I should make the refracted rays meet at a point. The point where refracted rays meet, there we are going to get the image. So at least two refracted rays should meet at a point. And that point will be nothing but the point where you get the image of the object. So to get the two or more refracted rays, we should know which are the rays we can consider to get the image. So let's see the rays that we can consider to get an image. So rays to be considered for image formation. For image formation. Okay. Let's see which are the rays we can consider for image formation. I will take the case of a convex lens as it is simple and easy to understand. So I've taken a convex lens here and I'm going to mark the principal axis. All this we have discussed in our last class. What is principal axis? What is optic center? The exact center of the lens, we call it as optic center. Okay, then this lens will have two focus, one on the left side, one on the right side, and exactly double of that I can call it as 2f, which will be there on both the sides. Now I want to see how to get an image, but for that I need to know what rays I can use, what rays I can consider to get the image. For mirrors, actually we have 4 rays which you can consider to get the image. For lens, we have 3 rays that can be considered to get the image. So which are those? Let's start. Any ray which is parallel to the principal axis, after refraction, you will find that the ray passes through the focus, which is on the other side. Not on the object side, but on the other side. So this is one ray which you can always use to get the image, one of the ray. At least minimum 2 you require, but here we are discussing 3. Any 2 you can choose to get the image. So this is the first one. Any ray which comes parallel to the principal axis after refraction has to pass through the focus. Second ray. A ray which passes through the optic center goes undeviated. So any ray, if you are taking it through the optic center, you don't have to show any refraction there because it goes undeviated. The third one. The third ray, a ray which passes through the first focus like this. After refraction, will come out parallel like this to the principal axis. So suppose you had an object over here. Suppose you had an object over here. And these three rays are coming from the tip of the object. That means the point where they meet also should be the tip of the same object. That means you're getting an image whose tip is over here. So this is how you get the image. So any any two rays you can consider for the image formation. Out of these three, whichever is easier for you, whichever you're comfortable with, you can choose those rays and you can get the image. This is for convex. What will you do if it's concave? Let's see what if it is concave. So say this is concave lens. This is a principal axis. The optic center. First focus. Second focus. First focus. Second focus. Actually, the measurements should be the same from here to here to here, from here to here. Length should be the same. Okay, now just I'm considering the ray, the image that you have to use to get the image, the rays that you are using to get the image. So I'm not really much bothered about the distances, but when we are really going for the image formation at different positions of the object, we will surely take care of those distances. Okay, yeah. First one. A ray which passes, which comes parallel to the principal axis. Now what will happen to this? It should pass through the focus if it was convex. But this is concave, right? It is diverging type. So the ray will diverge like this. But what if you extend it back, you will find that the ray seems to come from a point, and that point is nothing but the principal focus. So in this case, concave case, the focus is on the same side as the object. If you want, we can have an object also over here. Okay. The second ray which we are going to consider is the one which passes through the optic center, and there is no problem with that at all. Simple one this is. I will surely use this ray for construction of image every time because it's a straight line. Okay. So through the optic center, any ray passes will not get deviated at all. Okay. Then next one. A ray which passes through the first focus, comes out parallel to the principal axis, but here it will be, as you have observed till now, for convex and concave exactly things are reverse. So here don't think that it passes through the first focus and comes out parallel. It's not like that. Here it is something little different. It's something like a ray which appears to meet the second focus will come out parallel after refraction. So second focus is over here. So a ray which appears to reach that second focus, a ray which seems to be going towards the second focus, this ray, it looks like as if it is going to meet the second focus. focus. Such ray after refraction will come out parallel like this. So here also the rays passing through the focus but not really passing appears to pass through that focus, and this time second focus. In convex, if it was first focus, here it is second focus. Okay. So now, where are the refracted rays meeting? That point is the image, right? Where are the refracted rays meeting? If you see, this is one refracted ray, this is one refracted ray, this is one refracted ray. The three rays are not meeting at all on the right side. That means we have to make them meet somehow. So where shall we make them meet? We will make them meet on the other side. Okay, so we'll extend them back. The pink line is already extended back and it's reaching here. Let me extend the blue line back like this. And the yellow line is one single line, so nothing like extension. So finally, you see the three things meet at this point, and this point is the point where you get the image. So for concave lens, this is the only diagram you have, only case you have. Like you keep the object anywhere you want. You keep the object here or keep it over here or keep it anywhere. Okay. The image will be formed here itself. And it will be diminished only. No chance of having enlarged image. There's no other option here. Okay. This is the only option. You'll come to know that later. So slowly we will start drawing images for different object positions. For convex we will do first. For concave separately I don't have to. I'll tell you why. Yes. So now I'm taking convex lens and I'm going to draw the image for different object position. Yes. So this is the principal axis. This is the optic center. Take care of the distance F. I'm not really measuring it, but almost making it look geometrically proper. Double the distance is 2F. Exactly double the distance is 2F. Okay. Now I'm going to get the images. So image formation. Image formation in the case of convex lens. Image formation in the case of convex lens. First case I'm taking here for object at or object beyond 2F. Let's talk about object when it's kept beyond 2F. When the object is kept beyond 2F. So 2F is already here. So I'm keeping the object beyond 2F. Let me keep it somewhere here. Beyond 2F. Okay. As you know, you can use all the three rays or any two rays. Minimum two you require to get the image. I'll take only two rays. I'm not going to use all the three rays. Yes. The first one is the one which is parallel to the principal axis. This ray will pass through the focus after refraction. Another ray which passes through the optic center, nothing to worry about it. It has to go straight away like this. Goes undeviated. Please take care of the arrows also. If you don't put the arrows, there is no meaning for those lines actually. So in ray diagram, arrows are very, very important. If you don't mark the arrows, it doesn't mean that you are drawing a ray diagram. It's simple, a line, just a line. Okay. So that means these 2 points This is a point where the two rays are meeting. So this is a point where you get the image of the object. Okay, so this is the object and this is the image. Just observe where was the object, where you got the image, what is the nature of the image. Just observe that. We had kept the object, that's object distance u. We usually use the symbol u for object distance. Object distance is a distance from the object to the optic center. So this u is greater than 2f. So when we kept u greater than 2f, where we got the image, you just observe, it's between f and 2f. It's between f and 2f. So image distance we usually denote it by the symbol v. So it is v is between f and 2f. So it's greater than f, less than 2f. Within f and 2f you will get it. And what is the nature of the image? It is diminished. Diminished means what? Small in size. Okay, it became small, diminished. And it is inverted. Inverted. Usually inverted images are real. Real means you can catch it on a screen. Like if you bring a screen, a cardboard or something like that and keep it over here, this image, you will get it on that screen. Such images are called real images. Like for example, you see yourself on a mirror, in a mirror. If you keep a screen or something behind the mirror, can you get your image on the screen? Not possible, no? Or doesn't matter, you stand here, mirror is there, your reflection you can see on the mirror, you keep a screen over here. Does this go again reflect back and you get this image on the screen here, or cardboard or a white screen, anything you keep, you will not get, right? So those are virtual images. Those are virtual. So this is real. The one which you can catch it on the screen is real. Usually inverted images are usually real. Okay, most of the time. Yes. So this is the first case. When the object is beyond 2f, you get image between f and 2f. The image will be diminished, inverted and real. Second one, if you keep the object at 2f, let's see what happens. Just try it, students. Just try it. Give a try. Try. Okay, let me place the object at 2f. Let me take the rays. A ray which passes parallel to the principal axis after refraction passes through the focus. Another ray which passes through the optic center goes undeviated. So if you see here, the image, the two rays are meeting at this point. So you can see you're getting the image here itself. At what point you're getting the image? At 2f itself. And if you observe the size of the object and the size of the image, they seem to be the same. So that is what happens when you keep the object at 2f? When the object distance is 2f, image distance also is 2f, and image is of same size as that of object. Inverted, so it should be real. Inverted and real. So this is when the object is at 2f. Let's move further. Third case, when the object is kept, when the object distance is more than f but less than 2f. That means object is between f and 2f. Object is between f and 2f. Try this, students. Please try. Hope you got it. A ray which passes parallel to the principal axis after refraction passes through the focus. Okay. Second one, the one which passes through the optic center goes undeviated. Okay, so you get it like this. You do it with the proper measurement, you will get it. You should get it. So the 2 points, the 2 rays are meeting here at this point. So this is a point where you are supposed to get the image. So this is the object and this is the image of the object. If you see here, what do you find? The image size is a little bigger, so enlarged. Inverted, still inverted only, so it should be real. And you see, the image is beyond 2f. So when the object is between f and 2f, that's greater than f, less than 2f, image is beyond 2f. Image is found to be beyond 2f. So what type of image you get? Enlarged, inverted, and real. Fine. Next case. Let's move on to the next case, the fourth one. So here we are going to bring the object still forward, keep it at F. At F. Okay, let's keep it at F. Optic center, focus. Yeah. So now I'll keep the object at F. At F. So let me draw the rays. A ray which comes parallel, passes through the focus. The second one goes through the optic center, goes undeviated like this. You can see that these two appear to be parallel. They are parallel, so they will never meet here. That means if they meet, also it will be at infinity. They go to infinity. So if you have the object at F, image will be formed at infinity. And obviously you get an inverted here. Inverted, highly enlarged, real image. Highly enlarged real image. So that is what happens at F. One more case is there, that is between F and O, optic center. So what we had done is we had kept pushing the object front and front towards the lens. It was beyond 2F, then at F, then between F and 2F, then at F, and now between F and O. Let's go for between F and O. So between F and O. Draw the optic center. You can try, students. So optic center, focus to F, F to F. I'm keeping the object at between F and 2F. Sorry, F and O. So ray which comes parallel to the principal axis. After refraction, you know what should happen? You should pass through the first focus. Second focus. Second focus. And another ray which passes through the optic center goes undeviated. Again, it looks like the previous one, but in previous one they were exactly parallel, but these will diverge out, means they go away from each other like this. The gap increases. So that means they will never meet at the right side. Is it possible for the refracted rays to meet? Then any other chance is there? Yes, there is a chance. Only if you extend them backward, there is a chance that they can meet each other. So let's extend them backward. Extend them backward so that we get a chance to make them meet. So you can see we made them meet. We made them meet this way here. Okay, so this is a point where they meet. So this is the image actually. So this is the image. And this is the object. So what you can find here is image is on the same side as the object. So that means if you're seeing from this side, here, you will see that the object is also on that side and the image also you're getting on the same side. So it is obviously not a real image. It is inverted. It is virtual image. And one more thing to identify virtual image, you just check for whether it is a straight line or a dotted line. Means have you extended it somewhere backward? If you have done so, then that becomes a virtual object or a virtual image. Real one you will get by direct meeting. The rays directly meet at a point or they directly come from a point. If they are directly coming from a point, then that's a real object. If they are directly meeting at a point, then that is a real image. But if you have made it extend and look like coming from a point, then it is a virtual object. Or if you have made them look like meet at a point after refraction, then it is a virtual image. Okay, so whenever you use a dotted line and extend the things back, then it is virtual. So here the image is virtual image and the object is a real object, image is a virtual image, and image is enlarged. Here you can see enlarged, and it is lying, it's not, you cannot say like exactly at what position. It's on the same side as the object. It depends on like between F and O. If you vary the distance a little bit, then image position also will vary. But exactly where it will lie, it's not possible for us to say. Okay, so if you have the object between the optic center and the focus, this is O, okay, optic center and focus, then you get an image which is virtual, enlarged, and it is erect. Straight means erect. So erect, virtual and enlarged. So this is what you get when you have object between F and O. Okay, so these are the different cases in convex lens. Let's move on to concave lens then. I don't have to do it once again because it's the same thing what you're going to get again and again. I leave it to you. Okay, I leave it to you. You try with the different object position. You keep it anywhere you want, like at 2F, anywhere you want. You will see that the image is always between F and O only. It will be slightly varying the position, but between F and O only it will not come out of that. So you can try that. Okay, you can try that. You can keep this as a reference and you can try that. Anywhere you want, you keep it. So for concave, image is always between greater than O, but within F, less than F. O means optic center here. Okay, so it is always lying between that for any object distance. You can try 2-3 figures, you can try, and then you will get a confirmation that anywhere you keep the object, finally you will get the image between F and O itself. You can try that as homework. Yes, students. Next, let us talk about the equations, like if you know like where the object is, how to find out the where the image is. Like just now we saw the ray diagram. Yes, we get an idea like maybe the image is between F or within F or O, whatever it is. But exactly with number, if you want it, I give you that object is at a distance of 20 centimeter. I give the focal length of the lens or something like that, and I ask you what's the image distance, or I ask you what's the size of the image if I give the size of the object. So something like that, certain 2-3 factors if I give, and I ask you to find some other parameter using that. How to do it? Diagrammatically, yes, we get an idea, fine. But proper number if you want, proper value if you want. Obviously, you require some formula, right? So let's think about that formula. Yes, so we are going to learn a formula which is very useful for you. So you can find out anything like object distance, image distance, focal length, magnification, anything you can find out using any data given. But before we start with that, I need to talk about sign convention. Because whenever we are measuring some things, how to measure it first of all? Like if I have a lens like this, and this is the principal axis. Say I have an object like this here. Now I ask you to measure the object distance. Okay, so some of you may think of measuring like this is object, no, from here to here I'll measure and I'll say this is maybe 10 centimeter. Or some of you may say I'll measure from here to here and I may say 8 centimeter. Or some of you measure from midpoint to this, so it may be something like 9 centimeter. So from where exactly to do all the measurements is a big confusion now, right? And whenever I do the measurement, from where should I measure it? That's another important thing. From where do I measure it? Okay, yes. So to avoid that confusion only, we need a sign convention. Okay, then there are some measurements like you measure the things on the left side, you measure the things, sometimes image will be on the right side. So left side, right side, is it same meaning? No, you should be able to feel that there is something on the left side, something on the right side. The number should tell you that clearly, whether you are having an object on the left side or you are getting the image on the left side or the image on the right side. All that should be clarified in your answer, right? So for that, there should be a sign convention. So since there is left, right and all that, we need sign convention for that also. So let's go for the sign conventions. Let's understand the sign conventions and then we will proceed with getting a formula which is very, very important for us. Yes. So sign convention. Sign convention. First one, let's talk about from where to measure the things. Let's talk about that first. So sign convention, first thing, how to measure, from where to measure. So everything that you're measuring should start from the optic center. You should start measuring from the optic center. Hold the pencil at the optic center, then go left or right, wherever. So your measurements always start from the optic center and along the principal axis you should go. So not slanting up like this. Along the principal axis, only left or right you should move. It may be any distance. Okay, from the optic center, along the principal axis only you have to take the measurements. Okay. All distances are measured. All distances are measured from the optic center. All the distances are measured from the optic center along the principal axis. Along the principal axis. Along the principal axis. That's the first one. Second point now, when to take things positive, when to take things negative. If you are going in the direction of the incident ray, like if the incident ray was going like this and your measurement is also following that direction only, then things should be taken positive. If you're going in the reverse order, then it should be taken as negative. Any measurement it can be object distance, it can be image distance, it can be the focal length, it can be the radius of curvature, anything it can be, you should use that sign convention. Okay, so uh, distances distances measured distances measured along the incident ray direction distances measured along the incident ray direction are to be taken positive are to be taken positive and distances measured opposite to the incident ray direction are to be taken negative. Okay. The third one, speaking about the height. Heights also sometimes we require. Size of the image, size of the object. And some heights are above, some are inverted. So that also needs a sign convention. So any heights which are in the upward direction, they are taken positive. And the measurement is again along the, perpendicularly you are measuring it up or down like that. Okay. So any measurements upward, heights upward are taken positive, heights downward are taken negative. So you need to follow the sign convention every time you use it in a problem or anything. Any formula you use, that sign convention has to be applied. So keep this in mind when you are using it in problems and even some derivations also. So now coming to the very important thing, I told you that we require one formula to find out any parameter, whatever is asked. So we will do that now. The derivation, the formula which you are going to arrive at now is called Lenz formula. So let's derive that Lenz formula. Lenz formula. Let's start with the derivation. For which I need to draw a lens. I'll take a convex lens, which is always easier for us to understand. So this is a convex lens. I will draw the principal axis. So this is a principal axis. This is the optic center. This is a focus. Double the focus. This side focus. Double the focus. Okay. Now I'll keep an object. Anywhere you can keep, no problem. I'll keep the object beyond 2f. Like this. I will draw the ray. A ray which comes parallel to the principal axis. After refraction, passes through the focus. Another ray which passes through the optic center, goes undeviated. Okay. So this diagram is actually enough for us to move ahead. Just draw one dotted line. Okay. Now, there is image. Image is over here. This is the image. That's object. So object. Yeah. I'll call this object height as HO. And image height, I'll call it as HI. Okay, HO and HI. So now to begin with the derivation. Actually, we are going to get a relation between F, B and U. What is U? U is the object distance. Object is here. So this is the object distance. What is V? Image distance. Image is here. So this is image distance. So this is image distance. This is object distance from the optic center. Now we are measuring everything. So from the optic center to the object is object distance. From the optic center to the image is the image distance. Heights are taken as HO, HI. Focal length of the lens also let me mark it, because in the relation I need to have a focal length also. So the measurement from the principal focus to the optic center is focal length. Okay, let me start now with the derivation. If you see, there are some set of similar triangles in the figure here actually. I will take first one pair of similar triangle here. If you observe carefully, you can see over here. For this, there is one similar set like this. Can you see these two? The angle is 90 degree over here, 90 degree over here. These two being vertically opposite angles, they are equal. Can I say those two are similar triangles? Obviously, yes, right? So I will just name them because I want to write that those two triangles are similar. So I'll call this as AB and I'll call this as A dash B dash. So I can see that ABO triangle is similar to triangle A dash B dash O. So triangles ABO and A dash B dash O are similar. Okay, what if they are similar? You can take the side ratio. Side ratios are equal. So here, if I take from this triangle HO, from this triangle we have HI similar. So HO divided by HI, correspondingly this one if I take here, the horizontal length from here to here, can you see? From here to here, you have a length called AO, which is also equal to U in the first triangle, and correspondingly which side you have in the second triangle? A dash O. A dash O is nothing but V. Let's call this as equation 1. Then I can see one more set of similar triangles. One more set I can see. Which is that set? Let's see which is that set here. You see the set now here. I shade it fully. For this one, can you find a similar triangle? This triangle is similar to it. Correct, no? These two are perpendicular sides, I mean angles. These two are vertically opposite. So I can call them as similar. So you have here A dash, B dash, something here. What shall I? Yeah, F it is. This is F point. So A dash, B dash, F. And here OF, I'll call this as some C. Okay, these two are similar. So triangle, which are the triangles? COF and A dash, B dash, F are similar. So these two are similar. So what if they are similar? Again, go for the same thing. Sides ratio. Again, you know this is HI. Fine, no problem. But what is this? This is nothing but HO itself, because they are same size here, exactly parallel, right? And same length. So HO by HI, once again I get a ratio which is equal to now this time the horizontal lengths will be different now. See here, this is a horizontal length here, OF, and here it is A dash F. OF divided by A dash F. We'll write this in terms of U or V like how we did in the previous one. OF, how can I write it? OF. OF is nothing but F only, focal length. Focal length. Divided by A dash F. How shall I write this now? I know from here to here it is V. And I know from here to here it is F. I want this one. So from the full length, that is this, you remove this. You will get the remaining portion. So A dash F is this, which can be written as this minus this. That is O A dash minus OF. You can write this as O A dash minus OF, which is nothing but V minus F. We get the second equation. Now if you see first equation and second equation, just see the left hand side. HO by HI. Here also HO by HI. They both are equal on the left hand side. So the right hand side also should be equal. So we can now write V by U is equal to F divided by V minus F. We will just cross multiply like this. Or we can even do it this way. There are two ways. You can cross multiply and then divide it by UVF. I'll show you both the methods. I'll cross multiply UV minus this into this minus UF is equal to VF. So in this equation, what you can do is, you can divide the equation by UVF, dividing the entire equation by UVF. So when I divide this by UV divided by UVF, U and U cancel, UV cancels, 1 by F will be there. Here also this one I am dividing by UVF, U and F will cancel. Here VF dividing with UVF, so V will cancel, F will cancel. So you end up with the formula now, 1 by F minus 1 by V is equal to 1 by U. Remember, I have not still used any sign convention yet. I am going to do it at the end. So I get a relation 1 by F is equal to 1 by U plus 1 by V. Okay, I'll do the sign convention immediately. I told you I'll show you the other method also. Okay, so this is one thing when you cross multiply, or else we will just write the reciprocal reverse of this. That is V by U is equal to V minus F divided by F. We'll write it like this first. V by U is equal to V by F minus 1. That is separating the two terms. So what you can see here is, I will now divide the entire equation by V this time. So dividing thing will be there. So only by V I am dividing now. So when I divide this by V will cancel. What will be there is only 1 by U equal to, here also when I divide by V, 1 by F will be there. And here I divide by V, I get this. So I end up with the same equation, 1 by F is equal to 1 by U plus 1 by V. Now using the sign convention. This is alternate method. So using the sign convention now. We'll just check about F, V and U, which is positive, which is negative, we'll see. We'll see the diagram. Remember our sign conventions? All the distances that we have already done, no problem. We'll just see positive and negative. Along the incident ray, positive. Opposite to the incident ray, negative. So U is here. I am going to measure it from the optic center along the principal axis. So start from the optic center. Start going from here towards the object. So you are going in this direction. Okay, you are going in this direction. But the incident ray goes like this. Incident ray goes like this. So they are opposite. So U is negative. Fine. Let's see what happens to V. So V. Incident ray is like this. This is incident ray. Incident ray direction. Okay, this is incident ray direction. You start your measurement from the optic center, go towards the image. So you are going to the right and incident ray also is to the right. So this is positive. Then comes focal length. Focal length, there are two actually. One is this and one is this. You are supposed to concentrate on this one because this was included in our equation. Because focus, everything was, the meeting point was on the right side. So you start from the optic center. Focal length, focus is here. You start from the optic center, go towards the focus. So you're going to the right. So focal length also is positive. So only U is negative. V and F are positive. So from the sign convention, we have V positive, F positive, but U is negative. We'll put it there in the equation. Therefore, 1 by F is equal to 1 by V. And this is minus now. So minus 1 by U. So this is the final expression. This is called lens formula. Very useful formula when it comes to lens.